Mind your decisions, I'm Presh Talwalkar. How many balls are there? They say 95% get the wrong answer. For a challenge, write a formula if there are n layers of stacked balls. Pause the video if you'd like to give this problem a try, and when you're ready, keep watching to learn how to solve this problem. To get started, we'll review a famous formula. Suppose S is the sum of integers from 1 to n. We'll create a simple formula for the value of S. We'll first write the numbers in a vertical column, and we want to add up all the numbers in this column. To do that, we'll add a copy of S to itself. But here's the trick. Instead of writing the numbers from 1 to n, we'll write them in reverse order. Now let's see what happens when we sum S and S together. S plus S is equal to 2S. We can now add up row by row. The first row will be equal to n plus 1, the second row will be equal to n plus 1, and this pattern will continue, where every single row will be equal to n plus 1. Therefore, 2S will be the sum of these numbers in this column. There are exactly n rows that are equal to n plus 1. Therefore, 2S is equal to n multiplied by n plus 1. We can then solve for S by dividing both sides by 2. S is equal to n multiplied by n plus 1 all over 2. And that's the value for the sum of the integers from 1 to n. We'll now solve our problem. It will help to work with a 3D model. We'll first inspect the very bottom layer of this model. We can see the very bottom layer is a 4x4 grid of balls. We can then consider the other layers in this model. The very top layer will be just one ball. The next layer is a 2x2 grid of balls, and the third layer is a 3x3 grid of balls. If we continue this pattern, the nth layer will be an n by n grid of balls. In order to get the total number of balls, we want to count up the total sum of all of these numbers. The first number is 1 squared, and the nth row is equal to n squared. So we want to solve for the value of x, where x is the sum of squares of the integers from 1 to n. To do that, we'll use a geometric illustration. 1 is equal to 1 times 1, which is just 1. 2 is equal to 2 times 2, which is the sum of 2 copies of 2. 3 is equal to 3 times 3, which is the sum of 3 copies of 3. This pattern will continue, where we get all the way to n squared, which is equal to n times n, which is equal to n copies of n. We've created a triangle here. We want to add up all the numbers in this triangle. Now here comes the trick. We'll add 2 copies of this triangle to itself. Here's one copy of the triangle, and we'll rotate it 120 degrees counterclockwise. We'll then add another copy, which is rotated 120 degrees clockwise. We'll now add up these triangles element by element. So first consider the very top element. We have 1, n, and n. The sum will be 2n plus 1. If we continue this, actually every single element in this new triangle will have a value of 2n plus 1. You can go ahead and verify this for yourself, but trust me, every single value will be equal to 2n plus 1. Now recall, each triangle has a sum of x. Therefore, the resulting triangle will be equal to 3x. So what's this sum? Well, the first element is at the very top, and there's just one value of 2n plus 1. The next row will have 2 copies of 2n plus 1, and every subsequent row will have one more copy until the very end, which is n copies of 2n plus 1. So if we sum these numbers, we get 2n plus 1 multiplied by the sum of numbers from 1 to n. Now this is nice because we've already solved for this. It's equal to n multiplied by n plus 1 all over 2. We substitute that in, and then we rearrange this formula a little bit. We can then solve for x by dividing both sides by 3. And then we'll clean up this formula to get x is equal to n multiplied by n plus 1 multiplied by 2n plus 1 all over 6. And that's the formula if there are n layers. In the original picture, we had n is equal to 4, which would give x is equal to 30. But I think the fun is deriving the general formula geometrically, because geometric derivations are often more memorable than algebraic ones. This is a very fun viral problem. Thanks for making Mind Your Decisions one of the best channels on YouTube. As always, thanks for watching, and thanks for your support.